Good morning. Glad you're back. I know it was a interesting day yesterday, and we had to cut our talk a little short. So we're still in section 711, and I'm going to finish up day two. I want to look at this example. I just want to remind you that the two things that you should have in your notes at this point are question one and everything we did there, and the math notes, right? So at the bottom of this section, those math notes we discussed, and it's important that you understand those things that we talked about. So if for some reason you were unable to watch yesterday's talk, please go back and review that. So here we are, question two. It says examine the diagram at right. It's actually below. I moved it. The smaller triangle inside of the larger triangle is similar to the larger triangle. So we've discussed similarity yesterday, and it's important that we understand that we're talking about two different triangles here. There's one, and I'll kind of highlight this with this yellow. There's one that lives inside. It's this is the smaller triangle, but then we also have this larger one that I'll highlight in red. That's the entire thing, right? So there's two triangles here, and they're similar to each other. It might be useful to kind of break them apart into two. So here's the smaller triangle. This is the one that was in yellow. And then next to that, I'll write the larger triangle. That's like something like this here. And I could definitely fill in some information about these two triangles based on this original diagram. So I know that this is labeled 11.2. This is labeled M. They've labeled this side X. Over on the other side, the very bottom dimension here is 28. This entire side is not M or P, but it's M plus P. You can see both of those lengths, both M and P, make up this side. And then there's two things that make up this other leg here. There's an X and there is a 27. Okay? There's an X and there's a 27. So we are asked to use this idea of proportions to solve for x. So one thing, there is a scale factor here because we're told these are similar. And when we have similar polygons, that scale factor is the same when I go from any side and then I scale up or down. So let's say, for example, that the smaller one is it's the original ORIG, and that this is the new. And we said yesterday that the scale factor is the new dimension divided by the old. So it's this new over old, snow. Scale factor is new over old. And if I take a look at this, I could figure out the scale factor by taking the dimensions I know from both, right? I know this 28 and this is labeled 11.2, and it's the only side that's labeled on both. So I could say, oh, the scale factor equals the new dimension 28 divided by the old 11.2. And if I look at that, let's go ahead and take the 28. Oops, I got that wrong. 28 divided by 11.2. And that gives me 2.5. Okay, I'm going to hit math and I'll kick that to a fraction. It's 5/2. So my scale factor here is 5/2. And what's nice about that is I can take any of the dimensions in the original triangle, the x, the m, or the 11.2, and when I multiply those by the scale factor, I get the new corresponding dimension. So if I was to look at, let's look at these two. I'll label them in blue. So I'm going to go from this x to this dimension. And if I take the old one, the old dimension, which is x, and I multiply that by my scale factor of 5.2, I get the new dimension, which is x plus 27. And I don't think I've done this problem this way before, and I don't know why, because I'm liking how this is looking so far. So a dimension times the scale factor is the new dimension. All right. So if I take 11.2 and I multiply that by 5/2, I'm going to get 28. If I take x and I multiply that by 5/2, I'm going to get x plus 27. So what I am going to do now, I guess, is solve this for x. So if I was going to solve this, I guess I could take away x from both sides. So this is going to become x times 5 halves, or I don't like how I'm writing that. Let's write this as 5 halves x minus an x equals 27. Sure, if you say so. If I turn x into halves, this is 2 halves, isn't it? Yeah, so I've got 5 halves minus 2 halves, which is 3 halves x is 27. And if I want to solve for x here, one technique I could use is I could multiply both sides by the reciprocal. I could multiply both sides by 2/3. Because if I do that, here's my motivation. On this side, right, when I multiply the 2/3 times 3 halves, that becomes just x. I mean, it becomes 1. So I'm left over here with this x, and then equals 27 divided by 3 is 9. And 9 times 2 is 18. So I believe x is 18. So that's one of the sides I had to find. X is 18. Well, now that I know that x is 18, I probably, that's in the diagram. Oh yeah, they did show that these were right angles. Okay, that's fabulous. That's what I'll do. I'm probably going to now figure out what m is using the Pythagorean theorem. Okay, if you say so. Okay, so the big idea still here is that once I know the scale factor, I can take one of the original dimensions, multiply by that scale factor, and get the new. And I could definitely do something to go from m to m plus p, but the problem is I would have two variables. I would have m and m plus p. So I want to figure out what m is first, and I can figure out what m is. I can. The reason why I can figure it out is I can use the Pythagorean theorem and this triangle, because remember, we now know that this x, right, is the number 18. So if I was going to solve a right triangle that had, I'm trying to resketch the little triangle here. Solve a right triangle that had 11.2 and 18, and I want to figure out what this is, and it was labeled M in the diagram. What I would do is, okay, I'm going to say I've got leg squared. So one of my legs, the vertical one, that's the one that's going up and down, is 18 squared plus the other leg squared, which is 11.2 squared, equals the hypotenuse squared. And clearly the hypotenuse, it's always the longest side of a right triangle. It's the one across from the right angle. And in this case, it's labeled m. So I'll write m squared. So if I grab my calculator here, let's go ahead and take, let's see, clear. I'm going to take 18 and I'm going to square that, and then I'll go plus 11.2, and I'm going to square that also, and I get this number. Okay. So I get that 449.44 is exactly what m squared is. So there are actually two values of m that would work here, but in a geometric setting, I'm just going to use the positive one. So what I need to do is take the square root of that. So I'm going to take this, let me see how to do this. A second square root of, can I go grab that answer? No, I can't do that on this calculator. Okay, so I'm going to go the square root of 449.44. So when I take the square root of that, I get 21.2. So I get that 21.2 is what m is. Okay, that's fabulous. So we now know that this side is 21.2, and whatever the units are. In fact, this problem does mention the fact that there are no units here. It says, note that when no units are given on measurements, you may assume that all the units are the same. So I don't have to worry about some of them being feet and inches. They're all the same, whatever they are, but they've remained unitless. So now that I know what m is, and now that I know what x is, I can figure out the last piece here. And actually, I'm going to use the scale factor again. I like how that works. So again, the idea is if I take a dimension on the small triangle, which is m, oh no, but not m, right? This time, m I know is 21.2. Okay, so what I do is I take the dimension on the small triangle, and I'll label this with I haven't used I haven't, well, I'll use this. Oh, oh no, 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 no. Stop that. Thank you. I'll label this. This is the m, and this is the m plus p. So I'm trying to figure out what p is now, in case you're wondering, like, what are you doing? I'm trying to figure out what p is. So I'm going to say, I'm going to take the 21.2 from, that's m, and I'm going to multiply that by the scale factor of 5/2. Okay, and that should equal m plus p. But we know what m is, right? We just figured out m also. I mean, I already put m here, but I'm going to go ahead and say that's going to be 21.2 plus p. This is fabulous, right? Let me come back up here and kind of bring this home again so you can see the pattern. So you can see what we did with the x's, right? And I'm doing the same thing here. I'm taking m and I'm multiplying it by 5/2. And when I do that, I get what m plus p is. So that's it, right? I take a dimension on the smaller triangle. I multiply it by my scale factor. My scale factor is 5/2, and I get the new dimension, right? I get the m plus p. Well, I know what m is, right? M is 21.5. So I'm taking the m, multiplying it by 5/2, and then over here I'm getting 21 point, oh, not 21.5, 21.2. And 21.2. And then plus p. Well, this is great because I clearly can figure out what p is from that, right? So I'm going to just come in here and I'm going to say, I'm going to take the 21.2, I'm going to multiply that by 5/2. And that equals a particular number. Oh, that's 53 minus 21.2. And when I do that, I get 31.8. So I get that p equals 31.8. Okay, I know what p is. I know what p is. And and I also know the whole length of that side, right? That whole length of that side, this side that's labeled in green, it's the 21.2 plus 31.8. 21.2, that would be a 10, carry the 1, that's a 3, 3 and 53. So this whole thing is 53 units. So, and a couple internal checks, right? Now that I know what all the pieces are, right? I know what those are. I can do a little bit of checking. So it should be the case that if I take 18 and I multiply that by 5 divided by 5/2, I should get 53. I did not. So I've made a mistake somewhere. Let's think about this before I panic. Oh, no, 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 that makes absolutely no sense. So if I take 18 and I multiply that by 5/2, that should give me the length of x plus 27, right? Because those are the ones that are marked in blue. So if I take this blue dimension, am I writing here? If I take this blue dimension, if I take the blue thing and I multiply that 18 times 5/2, it should give me this bigger blue, the larged up, the increased one, right? The enlarged one. And that should be 18 plus 27. And yeah, if I take 18 plus 27, that does give me 45. Yeah, so 18 times 5/2 is 45. On the other one, m was, what did I figure out m was? M was 21.2. So if I take m, right, if we take this little m and we multiply that m times 5/2, we should get m plus p. And I can see m plus p is 53. So I'll take the 21.2, and when we multiply that by 5/2, we should get 53. Oh yeah, okay. I panicked for a moment. I thought, because to me everything has to be kind of internally consistent, right? If I start to see contradictions, I start questioning myself, like, where did I make a mistake? But I think that's okay. So this problem, there's probably there's many other techniques you could use to solve it. And if you come up with something you like better, please talk to me about that in class. It might be something that we work on later as well. Let's move on. So we talked about congruent polygons in terms of similar polygons, right? And we said that two polygons are congruent if they are similar and the scale factor is 1. Okay, if they're similar, That means all their angles match. We were told that also. If they're similar and the scale factor is 1. Well, here's another kind of way of thinking about what congruent polygons are. It says two polygons are congruent if one is the image of the other following a sequence of rigid transformations. And there's only the three, right? We can reflect, we can rotate, and we can translate. That is, there is a sequence of rigid transformations that map one of the polygons onto the other. So normally, this is actually quite nice to do with a piece of patty paper. And if you're kind of like more into developing an intuitive understanding of what's going on here, I would print this up. I mean, it's listed in our book as a PDF file. You could print up a copy, get out some wax paper or something, and kind of do some moving around on it. The thing that I find is most of these make sense, right? When I look at the question is which ones appear to be congruent. Well, if I was to trace this H, right, if I was to trace this onto the patty paper and just reflected it across some line, I could clearly see that it's going to match up with E. There's none of them have a right angle, so I don't think A goes with anything. Well, A is certainly similar to I, right? But it's a smaller version of it, so they're not congruent. I think that I'm pretty sure that K and F are congruent to each other, but I think you have to do a reflection there. So most of these things, and I'm pretty sure L and G go together. The one that's every single year it kind of catches us, and it's really convincing when you look at this with patty paper, is D and B. Just looking at this on the screen right here, I think to myself, well, clearly I got to be able to rotate and reflect and do something so those will line up. And I was I was trying to think about ways to visualize that. So I set it up in, I think this is not Desmos. I think this is GeoGebra. Yeah, I set it up so I can take D and I can do this rotation event with it, right? So I can rotate it, and if I rotate it, I can get it to where it's kind of lined up with what I think B is doing. So I just kind of rotate it so it looks like it's lined up. And then I can also do this translate where I move it down. And see, it's not quite rotated well there. Let me rotate it a bit more. Yeah, it's terrible. Even this, right? Even this, I'm looking at this right now, and I'm like, well, yeah, but if I flipped it over, if I did a reflection, it would line up. Well, it wouldn't. And the reason, I think the reason why is I think it has side lengths that are all the same, but the order switched. Like when you're going around, you go you go in slightly different orders, and it gets to where they're not the same. So I apologize. This is very uncompelling, but I just want you to know that just because things kind of look like they're congruent to each other, don't assume that, right? Really look at them closely, and when in doubt, sketching them out, looking at them with patty paper is it may be helpful to resolve any conflicts. So considering the definition of congruent polygons, why would it? So it says for each pair of congruent polygons, what would you say about the corresponding angle measures and side lengths? Well, I would say, based on the definition, that the corresponding angles are going to have the same number of degrees, right? They're going to be the same size, and the side lengths are going to have the same number of inches or millimeters or whatever we're measuring the sides in. So they would have to be equal. And two reasons, right? There is this transformation that maps one onto the other, so they have to line up perfectly. And this other idea that's playing around, they're similar to each other, and the scale factor is 1. So I know if I take one of the original sides and I multiply by the scale factor, if I'm multiplying by 1, it doesn't change the sizes, so they stay the same. All right, we're going to look at one more problem. Yeah, just this one more, 74. So in problem 73, we just concluded, I just heard you mumble, Mr. Roberts, that if two polygons are congruent, then the corresponding angle measures are equal and the corresponding side lengths are equal. Conversely, if two polygons have equal corresponding angle measures and equal corresponding side lengths, then the two polygons are congruent. So this is the first time that we've heard something, right, that sounds like a way to show that two triangles are congruent, right? So basically it says, hey, if two polygons have equal corresponding angles. So if all the corresponding angles have the same size, same measure, same number of degrees, and equal corresponding side lengths. So if the side lengths that are matched up together are also equal in length, then the polygons are congruent. Okay, so this is saying, hey, then they will be congruent, and you know that there will be a sequence of rigid transformations that will map one of them onto another. So this is kind of like the first time we're thinking like, well, how do we say that two triangles are congruent? And right now it's like to say it's going to take a lot of things. You have to show six things are true. You have to show that the angles are all the same size and the corresponding angles, so that's 3 with 3, and then the sides. So right here is this diagram, and it says, hey, sketch the triangles on your paper. Are the triangles congruent? If so, what is the sequence of rigid transformation that maps the triangles on the left to the one on the right? If the triangles are not congruent, explain. And then this is an important note. Note, the triangles are not drawn to scale. Okay, so I'm happy we're ending with this. So if we take a look at it, right, there's a couple things we know. Let me clear this out. So looking at the diagram alone, they didn't tell me they were congruent. They asked me, are they? And the problem I have is I clearly see I've got some angles, right? I've got this angle that's 90 degrees and it matches up with this angle that's 90. I've got one side here that's 16, right? And I got another over here, another side that's 16. But I don't have anything else, right? The angles that remain aren't the same size, and I don't know, and the other missing side, they're not the same size. So what do I do? What do I do? I'll tell you what I do. I know that the three angles in a triangle have to add up to 180 degrees. So if I look at this smaller triangle, right, I'm gonna say, well, let's take the 180 degrees. That's all three of the angles in this triangle, right? We're talking about this one. And I'm going to subtract from that the 90 degrees because I have a right angle. And I'm going to subtract from that the 75.75, that other angle I have. And when I do that, I get magic. I get that this angle up here at the top has to be 14.25, which is phenomenal because that matches exactly this angle right here, matches exactly this angle over here. So now I've got two, well, actually, and don't I have all three angles? I think so, because if I come along and say, well, let's do the same thing on the other triangle. If I take the 180, all the angles in the small triangle that appear small, I don't think it's any smaller, and I subtract the 90 from that, and then I subtract the 14.25, you can see that I end up getting 75.75, which is what okay, so if this, that means, whoops, let me get the black pen. That means this is 75.75. So if we look closely, what do we've got? Well, this angle right here matches this angle. So for these two polygons, they certainly have the property that all the angles match up and are congruent. The only question that remains is, do they have all three of the congruent sides? And I marked the one in green, but the question is, what about the other ones? Do they line up and are they actually congruent to each other? Just one moment. Okay, we just have a couple minutes left here. So what I want to do is figure out the missing sides. And it turns out, because we know the Pythagorean theorem, right, I can investigate with that. So I'm going to go ahead and look at this triangle first. And I've got two of the legs. And I know that in a right triangle, if I take a leg, 63, square that, and I take the other leg, 16, and I square that, I get the length of the hypotenuse. And I'm just going to arbitrarily say that that's, I'll call it H, I guess. That's clever. It's for hypotenuse. I don't know. I guess we use C a lot too, but I'm just going to say H. But you get H squared. So leg squared plus the other leg squared is the hypotenuse squared. So if I come along here and I grab my 63 and I square that, boom, and then I add to that the 16 squared, boom, I get 4,225. So 4,225 is exactly what H squared is. And if I take the square root of that, so I'm just going to hit second square root of 4,225. It should give me, okay, you see what just happened there? I just got that 65 is the length of H, so this is 65. So now that's an amazing thing. Did I run out of colors? I kind of ran out of colors. So let me do. Oh, I got purple still. So I know that this side length right here, this side is the same length as this side, right? So if you think about it now I have 5 of the things needed to show that the two triangles are congruent. I have all 3 of their corresponding angles are congruent, and I have 2 of their corresponding sides are congruent. And to just really put this down and say, oh, we're good, is I should, and I really think I don't need to, right? If I look at this, I'm going to make a prediction. This right here is going to be the number 63. It is. Because I can see from the other triangle, look, if I've got a leg of 16 and a hypotenuse of 65, a leg of 16 and a hypotenuse of 65, that other leg has to be 63. But I want to, what the heck, I want to show that with the Pythagorean theorem too. So I don't know this one, so I'm going to call this, I'll say that this is side B. So what I'm going to do is I'm going to say, look, a leg squared, that 16 is a leg, plus the other leg squared, right, B is a leg, equals the hypotenuse squared. So if I want to solve this for B, I'm going to say, well, B squared is what you get when you take 65 and you multiply it by itself, and then you subtract 16 from itself. And I really don't think there's a shortcut here. I really do need to do the squaring order of operation and then the difference. So I'm going to go ahead on my calculator, clear this. I'm going to say 65, and I'm going to square that, minus 16, and I'm going to square that, and I get exactly, okay, so I get that B squared equals 3,969. And if I take the square root of that number, the square root of 3,969, I get, that's what I wanted. I got that B has to be 63. So what's happened here is I've been able to establish that these two triangles are congruent to each other because I've shown all of the corresponding angles, right? The ones in the orangish, the blue right angles, and then the red angle are congruent. They all have the same number of degrees. And I've also shown that all of the corresponding sides have the same length. So even though this diagram didn't look like they were necessarily congruent, I can see, because I know that the angles have to add up to 180, and because I know the Pythagorean theorem, I can figure out more from this diagram, and I don't have to stress that out. There is one last thing that I do want to point out here, and it's this symbol, right? To represent the fact that two polygons are congruent, we use this symbol right here, this symbol, congruent. And when I see that congruent symbol, right, it tells me not only that they are congruent, but it tells me the parts that line up with each other. So if I was to write that triangle ABC is congruent to triangle DEF, I know 6 things from that statement, right? 6 pieces of info. This beautiful little compact statement tells me 6 things. And here's the things it tells me. It tells me that the measure of angle A, how many degrees it has, is going to be the same as the measure of angle B. That's true. Maybe I'm missing a step there, but that's true. And also that, oh, not B, measure of angle D. You can see that these parts go. So the part that's with A goes with D. The part that's with B goes with E. And angle C goes with angle F. So I can write all of those 3 statements. And then there's statements that relate the lengths of the sides. So for example, I could say this is how I write the length of segment AB. That's the length of segment AB. And the length of segment AB is the same length as DE. Right, and you can see I'm just taking the first and the second, Also, the length of BC is going to be equal in length to EF, And the final one that we have there is the AC. That's the one in the first and the last position, and then I go first and the last position. AC is going to go with DF. So yes, if two triangles are congruent and we're shown that, it literally means six things are true. And if I show that those six things are true, it forces the triangles to be congruent, right? These two statements are converses of each other, and a statement and its converse are both true here. Okay, so I'm gonna wrap it up there. And wow, look at this, 30 minutes. Are you kidding, Roberts? You can't say anything fast. Guys, I'll talk to you later. Do the homework assignment now, 4711. Now that we're complete, I didn't assign it yesterday, but go ahead and do those problems as well. And thanks for stopping by. I'm glad you were here, and I hope you're okay.